Sorry, I'm all backwards today. Okay. We're recording, but I can't get my PowerPoint up. I use PowerPoint to have a window to write on. So while this is trying to come up, PowerPoint is so stinking slow. Any questions on anything we've done so far? Oh, I forgot to mark you here. Then you can ask a question. Okay. Happy February 1st. Okay. By the way, I got one paper graded, but I didn't get a chance to do the second one. I don't have it in Blackboard yet, but even though they're not graded, you get credit for turning them in January. So, well, finally, the PowerPoint is starting to start.
What you think about the paper?
Second.
What you think about the paper?
Oh, it was good. I enjoyed it. The first one, the one for this class, very good. And
I thought the one for capitals was a little bit more interesting.
okay, I haven't read that one yet. So.
That was about EID controllers.
Oh, okay, great.
I found it difficult to understand parts.
Uh huh.
I found some parts difficult.
You what?
Found some parts difficult to understand.
Yeah. Basically, even the name sounds like they may be. So, okay. We're recording. I've almost got the slideshow set up. Yuck, this is taking forever. There we go. I think we're ready to go now. With one small exception. Let me get my pen activated for black. Okay. So, no questions on what we've done so far. Oh, man. I think I left my paper in the page we had done previously and not in how far we got. So let me see. Yeah, it was the, well, I thought we were on 30, Kirchhoff's Law.
Well, we were doing the...
Right, and we finished that, didn't we? Or did we? Oh, no, I said take it home and finish it.
Yeah.
How was it?
I messed up somewhere.
Okay.
Rewriting all the numbers.
Right, and that is, to me, the biggest problem with matrix operations is, man, it's just tedious, boring. So, but it's powerful. But that's why you get a computer to do it, as long as you program it right, you know. But yeah, they will do it and do it well. You want me to pick up from where we left off and go from there? Second?
However you want it. It's
Yeah.
simple how to solve it.
What's that?
It's simple how to solve it. You just have to keep up with all the numbers.
Right. Yeah, but you don't have any conceptual issues.
No.
Okay. All right, well, let's go on to another one then. And it's sort of a follow-up to that. In example 5, the one we just did, you could control the amount of flow along a branch X5. Oh, they don't show the same picture. X5 was the one at the bottom. And suppose you could do that. And then using your solution for example 5, you could then control the flow represented by each of the other variables. And so it shows how to do that too. But since we don't have the matrix in front of us, we won't do that. But it just, what they're trying to get at is, once you have it, the matrix working and stuff like this, then you can start playing with it, you know, and doing things. And I'm not absolutely certain, but I wouldn't be at all surprised if drug research doesn't use matrix, this kind of manipulation of matrices. If they know they've got to, say, on a cancer cell, they're trying to inhibit a protein that's part of an enzyme that gives the unregulated growth of the cancer cells. And they know if they can stop that, we have a good chance of stopping the cancer in its track. Then by knowing molecular bonds and things like this, they can it's almost just like a junction analysis, you know, and put that in and say, well, if we did this, would that work? If we did this, would that, and study and see what the influences on the other things would be. So then at the end, you know whether it works or not, or at least theoretically. And then you also might be able to control side effects because you're seeing what it does to all the other things. So, boy, if you think in that term, pretty powerful stuff, you know. So that's just, I'm not even sure they do, but I wouldn't be at all surprised that's not what they use. Okay, Kirchhoff's laws, and you haven't had physics yet, or, okay. So this is sort of new to you. The others, I think, had it. Kirchhoff's two laws, these are electrical networks, okay? And you were doing controllers, you said, in your paper, okay? This doesn't have controllers in them, but you can almost imagine you could stick these things in. Here's the two laws. All current flowing through or into a junction must flow out of the junction. We don't have any junction seats that can collect currents. That would be called a capacitor, but no, we don't have that, okay? So, and then number two, the sum of the products, okay? Now, this is a math person writing. The sum of the products IR, okay, around a closed path is equal to the total voltage in the path. Well, the products IR, that is a voltage. That's a voltage loss due to resistance, right? Okay? Ohm's law, okay? V equal IR, okay? So, the sum of all the voltage losses must equal the input voltage into that loop. And now they call it closed path. I call it loop, okay? So, that's what we're meaning. And just for a little background here, the current is measured in amps, named after Louis Ampere, so it's a capital A, that's for current. The symbol for current is I. The unit for current is amp, okay? The symbol for resistance is R, that's sort of the parameter. The unit for resistance is ohm, named after Georg Ohm, who did a lot of the early work in resistance. So we've used A for ampere, named after Ampere, named the amp after him, or Ampere. What would you use for ohm? Say again? Say again? Yeah, okay, but OH, is that what you said, or spell it out? What symbol would you use for that unit? Just O, is that what you're saying? Okay. Yeah, why wouldn't we use O? His name starts with O. It looks like a zero, so we couldn't use that. So they went to the Greek alphabet. And the Greek letter corresponding to O in the English alphabet is Omicron. But guess how Omicron looks? A capital O. So that doesn't work either. But there is another letter in the Greek alphabet that starts with the letter O, but it's not where O normally is. It's the very end of the alphabet, omega. Have you ever heard the phrase, the alpha and the omega, beginning and end? Okay. Alpha is the first letter in the Greek alphabet. Omega is the last letter. That's what that means. So we use, but not a little omega, because it's named after a person. We use a capital omega, which looks like that. And that's the symbol for resistance. Now, I hate to take class time for it, but it's just almost too bright to pass up. There is an inverse concept in the physics of circuitry, other than resistance. It's called conductance, which is the reciprocal of resistance. So conductance is equal to 1 over the resistance. And sometimes it's more convenient to, not in these problems, but in other problems, to talk about conductance of a circuit, not resistance of a circuit. So what unit, by the way, resistance is measured in ohms, O-H-M. Okay, so what do you think the unit that they use for conductance is? You have any idea? Okay, I'll tell you what it is. It is a mode. Now, was that developed by Frederick Moe? No. Say again? They spelled ohm backwards. Physics is sort of strange, you know. Now, what unit would you use for that? Maybe capital M? Well, we already are using a capital M for a mega, you know, the prefix for 10 to the 6. So that would get a little confusing. What could we use for the symbol for mode? Go to the Greek alphabet? No, probably not. Well, sort of, yes. That's the symbol they use for it. There is no symbol like that. What did they do? They took the omega and did the reciprocal of it, flipped it upside down. Physicists are really strange. Okay? Totally. Okay. So that's too much of that. Whoa, it didn't erase. There we go. All right, enough of that. And then this is sort of one of the strangest things, well, we've already seen so many strange things in physics. The other is voltage or potential difference. It's called voltage, so the parameter is V. Guess what the unit is? Volts. Okay, also V. So in that one, the parameter, the thing that represents it in an equation, is the same as the unit that you use after your numbers. Rather bizarre. And by the way, that was named after Volta, who was an Italian physicist who did some of the early work in batteries and stuff. So they named it after him. Unfortunately, I got to go when my wife had a professional meeting in Lake Como, Italy, which is right up next to Switzerland, almost, you know, way up there in that part of Italy. And we were, our niece was with us, so while Karen was busy in meetings, we were just touring the city. We saw this beautiful, almost temple-like structure out here just overlooking the Lake Como. So we walked out to that. It was fairly close to where we were staying. And it was a shrine, basically, to Volta, because that's where he was from, Lake Como. So, and it had a lot of his, you know, original batteries that he had put together and stuff. Really was pretty fascinating. But enough of that. All right, now some symbology, okay? When you're talking about potential difference or voltage, usually they use a symbol like this. I'll put it the same way they do in the book, okay? Symbol like that. Now, what that stands for, every battery has to have two plates, positive plate and the negative plate, okay? So the convention is to make the positive plate the big line and the other plate the little line. So this would be the plus side of that battery, and this would be the minus side. Now, and you might think this wouldn't happen, but, oh, and there's all sorts of crazy things about circuitry. In all of physics and in all of nature, we always talk about things going from high potential to low potential. That's how things do. I lift the book into the air, release it, and it doesn't float upward. It floats downward. It falls downward because the gravitational potential is greater up here than it is here, so it's going to move in the direction of decreasing potential. And that works in everything in physics, you know. In life, I mean, that's what it does. With one little problem. I think some people blame it on Benjamin Franklin. Back when electricity was first being studied and understood, and they figured out it was a movement of charges, and they knew there had to be two charges, one positive, one negative. I've heard it said that Franklin was the one who recommended, well, why don't we make the proton positive and the electron negative? Okay? Fine. I mean, why not? It's sort of arbitrary choice, right? Except that when you have a battery, yes, the electron flow, which really isn't the important thing, but the electron flow would be from negative to positive, which is going up in potential, whereas the conventional flow goes in the other way. So if we and actually you can send current against the battery. If you have a bigger battery somewhere else, turn the other way, it will force current across it. So if you had current going this way in the battery, that would be a negative current. If you had it going this way, which is the way it would want to go, positive. But that's the conventional current going up in potential. So, all this stuff. Okay. Now, rest of the symbology. This symbol indicates a resistor. So this would be your voltage. This will be your resistance. Okay. Now, the other thing, of course, the lines here represent wires. That's where the current goes. So usually you just indicate the current, and you indicate the direction for the current. That's what I was doing there. So those are what you sort of need to know in these symbols. So let's look at example 6. I'll erase all this stuff and get to example 6. Here we have a circuit. Okay. Okay, there we have a circuit. I think I got it right. Okay, now here's a resistor. We'll call this resistor R1, and that is a 3 ohm resistor. By the way, they've chosen easy numbers to work with. A lot of times you don't have 3 ohm resistors. I mean, that's not much resistance at all. You would have several hundred or 1,000 ohm resistor, K ohm, kilo ohms. So. But we'll just for this purpose. Here you have a voltage source. Okay, I'll call this V1, and that's going to be 7 volts. Notice that 7 volts going in that direction. Okay, but we'll get to that later. Here we have R2. And this is a 2 ohm resistor, which is almost no resistance at all. It is some, but not a lot. By the way, 7 volts is not a huge voltage either, but it's significant. I mean, it's reasonable. And here we have the third resistor, R3, and this is a 4 ohm resistor. And here we have V2, power supply 2, or electromotive force 2, or potential difference 2, whatever you want to call that, and that's 8 volts. And again, it seems to be going in that direction. All right. Now, other things to note here. Okay? You have 2 nodes here. You got a lot of corners, but what a node or a junction is where current could come in and go out. Okay? Now, that's not a node. You could bend this around, you could straighten that out. It wouldn't be a node, okay, or a junction. That's a junction, that's a junction. So you only have 2 junctions, so they number or list these as 1 and 2. Goodness gracious. 1 and 2, like that. Okay? Now, we also have several loops, okay? Or pathways, I think, closed paths. There's 3 actually. You could have a loop that goes around like this, a loop that goes around like this, or a loop that goes around the outside. So there's 3 potential pathways, closed pathways that you could do. Now they only mentioned 2 of them, so we'll stay with their 2. And they went path 1, and they actually give this a direction too. I'm going to do what they did and choose a different color. They used baby blue, so let me do that too. Okay, that is what they call path 1. That just means a pathway 1. And this is what they're calling path 2. Okay? Now, by giving those directions, and they look like they're reasonable directions on it, okay, until you get, if you were dealing with the third path, something has to give. Okay? If the third path, either it's going that way, which is going against the flow there, or it's going this way, which would be going against the flow here. So we're not worrying about that. Since we're not choosing that as a path, we're going to use these two paths here. And this may work out fine. Okay. Now, remember Kirchhoff's two laws, the junction laws and the path laws, closed loop laws. Okay? The first says, okay, right, okay. I forgot to label one more thing. And let me make sure I do it the same way they do theirs. Yeah. Now, they put it over the resistances. You don't have to. It seems like that's sort of crowded there. So I think I'll go back to black here. Okay. Put my arrow here that corresponds to that pathway and put I1. Okay? That's the direction we have the path going. So we'll say that's I1. Now, they choose I2 as this other one down here, and since I got more room here, both of these indicate I2 would be going this way. So the I2, right? And in the third one, it looks like I3 is going in this way. Okay. Now, to be going in the direction. They don't put arrows on theirs, they just say the current through that. And then they follow the path, okay? So, want to start with the junctions? Okay, or nodes, I like to call them nodes. Let's start with one. What does this tell you? Now, maybe I should have put my I over here too. This is I2. Same current that's here has to go through all this, so that's I2 in that middle section there, okay? If I put it there for hopefully instructive purposes. Now, I don't really care for the way they phrase it here. All the current flowing into a junction must flow out of it. Yeah, that makes sense. The other way to express that, and the way that we want to express it, is the sum of all the currents into a junction is 0. Those coming in are positive, those leaving are negative. The sum has to be 0. It says the same thing, right? Okay. So you tell me an equation that says that. Starting here with I1. That's going into 1, so that would be I1 minus I2 plus I3 is equal to 0. Very good. Gag. Okay. All right. Let me clean that up just a little bit. Okay. Ew, too much. Okay. Now, how about junction number 2? And here we have, just for reference here, here's still I1 going this way, and I3 is going this way. Say that again. You're starting with I3? Huh? I2, okay, positive I2. See, I'm trying to set it up for my matrix, okay? Minus I1. Okay. Minus I3 equals 0. Guess what? They're really saying the same thing, aren't they? One just has the positive, one has the negative. So that's not two independent equations. They are two equations, they're two true equations, but really they're saying the same thing. So that's not, those are dependent. Let's just leave off the second one, okay? So we are going to need at least two pathways. And we'll need Nigel to get here. Okay, what is it? That's what everybody has said this morning, me too. So what we're going to do, but he already knows all this because he's already had his physics, right? Ooh, it didn't do it again. Okay. we're doing Kirchhoff's law on this circuit here. Okay, we just did the nodes and found out both nodes told us the same thing, so I erased the second. Let's go to path 1. Okay? Okay. Now, I like to go around in the direction of the path. And if you have, remember, I1 is going through R1, I2 is going through R2, and I3 is coming through R3. Okay? So in path 1, if we follow that along, I think what I'm going to do is write it down here, and then I'll translate it over there. Okay? I like to start at my battery. Not necessarily why, but if the path's going that way, what's happening to the voltage as you go from here to here across that battery? Goes up 7 volts, right? That's what that means. Your potential difference increases by 7. So that is, and that's what Kirchhoff's second law says, the sum of the products, IR, which are voltages, is equal to, is a voltage equation. The junction law is a current equation. This is a voltage equation. So this says V1, and then what's the next thing that happens? As you go along that pathway, what do you run into? A resistance. And every time you go across the direct resistance in the direction the current's going, you're dropping in voltage. Okay? So that would then be a minus I1 R1. Right? And then what happens along path 1? The nodes don't lose anything. The wires we assume is no resistance. You come back around, and then what do you hit next? You get a minus, well, yeah, you drop there too because you have the direction of I2 in that direction. That was arbitrary, but we chose it. So that would be minus I2 R2. And then you're back where you started, so that's equal to 0. Right? Now, let's plug in the numbers we know. What will this be? V1, 7, minus, now we know, say again? Okay. We don't know anything about I1. That's what we're looking for. We do know that R1 is 3, so that's minus 3I1, right? And then you get down here and you get, you know R2, but you don't know I2, minus 2I2. And that's equal to 0. By that? Okay. Now, let's go back and put it in the order we want for our matrix, right? Okay. Now, I just as soon have a positive I1. I don't have to have it, but I like it. You know, it makes me feel warm and fuzzy. So I'm going to move these to the other side because these are my variable parts. There's my constant part, and that would be 3I1 plus 2I2 equal, plus 0 is equal to 7. I left that on the other side, right? Okay, let's do the second pathway. This time I'm going to start down here at the voltage there, and that's going to be at V2. That's going to be V2. You're going up in voltage as you go around the pathway in that direction. V2, you tell me. What's next? Follow the path. Second? What about it? I3. Oh, minus I3, R3. Okay. Follow the path. What you get? Minus I2, R2. Sorry about that. Okay. And you're back where you started. Okay, I don't know why the whole thing. Erase. Okay. All right. And you're back where you started, so that's 0. All right, let's plug in the numbers there. V2 is 8 minus 4I3 minus 2I2 equals 0. Now let's get that back in the order we want it for our matrix, and what would that be? 4. Ooh, I'm writing in the wrong place, am I not? Okay, sorry. Okay. Yeah, and that's going to be a positive 4I3. So plus 4I3. And Jonathan's here. All right. Just missing Marcus. If we get Marcus there, perfect attendance. Hope that happens. What's next? Got the 4I3 in there. You may be saying, I can't hear, my hearing's bad. 2I2. You could put a plus in front of that if you wanted to, and that's equal to 8. Okay. Feel like a dentist here? Okay. We have 3 equations, 3 unknowns. Don't think we'll need the third loop. I think that would just replicate what we've already got. So what's your next step? Write it as a matrix. And what would that matrix be? 1 minus 1, 1, 0. Next. 3, 2, 0, 7. Next. 0, 2, 4, 8. All right. Now, you want 1 in the upper left, and we got it. Fantastic. Okay. Say again? We want 0 underneath it, so how do we make that happen? -3 R1 plus R2. Okay? So we're using the first row, so we write it down. 1 minus 1, 1, 0. Okay? What's your new second row? 0. Okay, I could have done that one. Okay, what next? 5. Negative what? 3. One more time. Okay. Height. Okay. 7. Okay. Now, is there anything else you'd like to do maybe? Hint, hint. Yeah, let's divide that third row by 2. Okay, because everything's divisible by 2. So row 3 divided by 2 is the new row 3. So when I write it down, it's going to be 0, 1, 2, 4. Okay, you see sort of why I want to do that? Okay, because what's the next thing you want to happen? Yeah, you want there to be a first non-zero entry here to be a 1. It's a 5. To get that to become a 1, you have to divide by 5, which is fine here. That gives you a -3/5 here, and a 7/5 there, and I know Nigel loves his fractions, but I don't that much, okay? So it's much easier to flip these two. That gives you 1 right there with all whole numbers. You don't have to fiddle with fractions, though we love doing it. Okay. So we're going to reverse these 2 rows. I hate to write down the whole matrix for that, but we'll do it. 1 minus 1, 1, 0. New second row is, I should write this, row 2 interchanges with row 3. Thing drives me nuts. Okay. And that would be 0, 1, 2, 4. And the next one would be 0, 5, -3, 7. All right. Now what do we want to happen? Second? The 5 to be a 0, but we also want the -1 to be a 0. We're doing Gauss-Jordan. We're doing reduced row echelon form. Because what I want to do is just read the answers. Because I'm really lazy. No, I'm lazy. Okay. So what do we do to get a 0 up there? Yes, row 2 plus row 1 is the new row 1. Doesn't matter which way you say it, but we typically say it, the one you're operating with multiplied, but yeah, never mind. So, what was that new? We're using row 2, so that's 0, 1, 2, 4. So I don't fiddle with it and mess something up. What's my new row 1? 1, 0, 3, 4. Okay? What are we going to do next? Yep, and how do we do that? -5 row 2 plus row 3. And what does that become? First entry? Second? It stays a 0, of course, because you multiply -5 times 0 plus 0, still 0. Next? 0, that's what we wanted. Next? -13, you said? Okay, and next? Again, -13 again? Is that what you said? I can't hear well. Okay. Very good. Now, what next comes to mind? Yes, and how do we make that happen? Divide everything in the third row by -13. So row 3 divided by -13. Not a very pretty number, but it's okay. What does that give us? 0, 0, 1. Now I'm going to cheat. Yes? Yeah, that's what we want. And we want this to be 1, 1, 1. So
Okay.
therefore we want that to be a 1.
Make sure it's still
Huh?
So I'll make sure
Yeah.
it's still
Now, I don't know, I know you weren't here last time. Did we do reduce row echelon form before, while you were here? Or okay.
We did that.
Yeah, we're doing above and below now. Before, we were just doing Gauss method, which is just getting the zeros below it. We'll have another name for that later. But yeah, we're trying to get that to be a 1. So we divide by -13. And watch my magic here. -13 divided by -13 becomes 1. Oops. I thought I had my eraser doing. So that'd be 1. And -13 divided by -13 is 1. There, I did it. Okay. Y'all have to write it out. I can just use magic pen. Okay. What do we want to happen next? Okay. I need some more room. And I think I'm going to come to the left here and wipe out my scratch work. Is that okay? It's my screen. I can do whatever I want. But is that where you like to do it? Okay. All right. So let's wipe this out. I say I can do whatever I want. It's really slow at erasing now. Okay. Okay. Get my pen back. Okay. Now, so what do we want next? Let's just do a quicker review. We want a 1 here, 0 below, done. 1 here, 0 above and below, done. 1 here, done. Now what? 0's above. How do we make that happen? How about in the first row? Negative 3 times row 3 plus row 1. All right? Let's do that next. We're coming way over here. Okay? So we're using the third row, 0, 0, 1, 1. And by the way, just a little time out here. What does this third row tell us already? That stands for your I3 is equal to 1 amp. That's what it tells you. And we could start doing back substitution, but we're too lazy to do that. We're going to let the matrices take care of it. So we're going to do what he told us Emmanuel said to do, is minus 3 row 3 plus row 1. And what does your first entry become? 1. Second entry? Third entry? 0. That was easy. Now, the one that really matters, what does that mean? That's a minus 3 plus 4 is 1. So that tells us I1 is also 1. Well, this doesn't look very exciting, does it? What do we want to happen next? 2 become a 0. How do we make that happen? I'm going to write it over here. Negative 2 row 3 plus row 2. All right? And what does that give us? 0, a 1, a 0, and what? 2. So what does this tell us? Just read off the top. I1 is equal to 1 amp. I2 is equal to 2 amps. And I3 is equal to 1 amp. Okay? Now, I like just to look up here and say, does that even make sense? Well, you got I1 coming in here at 1 amp and I3 coming in here at 1 amp, I2 leaving at 2 amps. Yes, that looks perfect. Of course, the same thing happens at the second node or junction. And then we just use those equations, so it better work that way too. You can go back and check everything, but by and large, I think you'll be fine. Okay.
So, basically
Yeah.
all you did was like simplify the
What's that now?
So basically all you did was like simplify.
Yeah, you're trying to, and that's what your reduced row reduction does. It comes as close as it can to getting 1s on diagonals and 0s everywhere else. And then, unless you have a column in here that doesn't have a leading 1, and that can happen, then you have a parametric equation. But if you have them like this, remember, the columns stand for your currents, and the rows stand for your equations. Now we use 1 Kirchhoff's junction equation and 2 Kirchhoff's closed path equations. Okay? That's where we began, that's how we ended, and sure, it looks like it makes good sense. Okay? That answer what you needed? Yeah. All right. 1, 2, and 1. Got it. Let's do example 7. Ready for that? You need this up a little longer?
No, I haven't.
Okay. All right. What's that? Okay. Okay. Let's go to example 7. Oh my goodness, this is going to take a while to draw, isn't it? Let's start right up here, and if we go down here, we hit a 10-volt power supply or battery, okay? 10 volts, okay? If you keep on going down, we run into a resistor, okay? And that is R1 is 2 ohms. R1 equal 2 ohms. Okay. Now, just to get things moving along here, we hit a junction here, and they call that junction 1. And from junction 1, by the way, they named the current that's flowing through here I1. Okay? And we're assuming it's flowing downhill. Okay? because battery pushes it that way. Okay, here we have a place, goes up from here and hits another resistor, and this is R2, and R2 is 4 ohms. All right, goes up to junction number 2. Okay, now keeps on going out here from 1, and by the way, they named this current I2. I like to put an error on it. Now they didn't indicate an error, but you see, yeah, they did. They have a little bitty error there, but they don't write it by the I1. I wish they did. You know, that's why I do it the way I do it. Okay. After 2 here, let's go back up to 2, we run into another battery. Here's the downside, and there's the upside. And this happens to be 17 volts. Okay. And then we hit another resistor, and this is R4 as a 2 ohm resistor. Okay. And then we hit junction 4. So we're not doing it in the same order they did. I was down here on 1. I forgot that. And ran into a resistor here. And this is R3 is equal to 1 ohm. Okay. And by the way, they have, I'll come back to that in just a minute. Let me finish my drawing. Okay. Come down here and hit another resistor. And we call this resistor R5. And R5 is a 2 ohm resistor. Okay. And we hit a junction number 3 down here. Okay. And then from 3 it goes over here and goes up. And it doesn't really matter whether it's going up or down. It doesn't matter. And it hits another resistor, which we're calling R6, which is a 4 ohm resistor. Okay. And hits another battery. Boy, this is a complicated circuit. And this, that's kind of weird. But this is a 14 volt battery there. All right. And then it goes on up and closes out here to 4. Okay. Do I have everything in place? Not quite. I have my I1. We see it goes everywhere along there. We have our I2. That was easy. They put the I3 down here, so I'll do the same thing they did. Now, they chose I3 to be going this way. I3, okay? Now, okay, no real reason not to. Got to go some direction. We'll have it going that way, okay? I5 is the one over here. Sounds like an interstate, doesn't it? Okay. And they have that going downhill as I5. Okay. Fine. I don't see any problem with that. Okay. And then they have I6 over here going up. I6. And that looks reasonable. And that's what we're going to do there. So, yeah, 14 volts seems to be pumping it up that way. That would make sense. Okay. Now, pretty complicated looking deal here. I think I've got everything listed. Do I? No, I don't. I have I4 missing. Is that what you're saying? Yeah. And I4 they have going, yeah, away from the battery here. So I'm going to write it here, I4 in that direction. Okay. Now I think I've got them. That's what I was just looking at. I1, 2, 3, 4, 5, and 6. R1, 2, 3, 4, 5, and 6. Now you don't always have to have a separate, well, maybe you could have 2 resistors within a loop, so you don't have to have the subscripts matching. So far these have matched pretty well. Okay. So, which Kirchhoff law you want to do first? is its first law? Junction law. So let's take junction 1, since it's number 1. Okay? And what we're doing is looking at the currents coming in or out of the junctions. Okay? And what current do you see, say, coming into the junction first? How about good old I1's coming in, right? Because if it's that there, it's also here, right? So there's I1. So let's say I1's coming into that junction. What seems to be leaving the junction? Okay, I2 is leaving the junction, so minus I2, right? What's I3 doing? It's coming into the junction, so that's, say, plus I3. We'll leave a little bit of space there, and the sum of all the currents coming or leaving a junction has to be 0, because no junction can store current. You know, it has to get rid of anything that comes in, so that's 0. Okay? Let's go to junction 2. And what do you see happening at junction 2? Okay, how about let's starting with I1 here. There's I1. There's nothing. Say again, yeah, that's leaving it. So that's a minus I1. Plus I2. And then we've got I3 doesn't do anything to junction 2. Here's I4 here. That's I4. All along that line, that's I4. It's leaving it, right? You see that? Here's the junction. I1's leaving, I2's coming in, I4's leaving. So you got a minus I4. And that's equal to 0, because the sum of all the currents coming and going have to be 0. You can't store current at a junction. Okay, let's go down to junction 3. What do we have going on there? I3 is leaving the station. That's a minus I3. I5's coming in, so that's a plus I5. And I6 is leaving, so minus I6 is equal to 0. I didn't leave enough room, did I? Okay, let's go up to junction number 4. What's going on there? I4 is coming in, so there's a plus I4. I5 is going out, so that's a minus I5. And I6 is coming in, so that's a plus I6. So that's equal to 0. I6 is here, and it's always, current can't turn around on you.
Oh, okay. I thought a little space moving out.
Say again?
I said the space moving out.
Oh, that right up here? That's your battery. That's what's pumping.
Okay.
Yeah, that's what's moving along. Okay. Okay. Well, we have 4 equations with 6 unknowns. We will need some loops here. We have we have lots of loops. We have a closed loop in here, a closed loop in here, a closed loop in here. We have a closed loop here. We have a closed loop here. And we have an outside loop. Now, we sure don't need all those. And I think if you really think about it hard, you'll get a headache. No, I mean, you'll say, I think some of those have to be dependent on each other. So let's try to get 3 that look like they'll be sort of independent. Not that 3 is a magic number. It seems like 2 would do, but 3 is pretty easy. Just do the loops that you see. And you get to choose which direction you think those loops are going. what would you say? They call them paths, so I'll call them paths. They like baby blue here. What would path 1 be? I take that 10 ohm and I say it looks like it's pumping it that direction, doesn't it? So let's call that path 1. Okay? Over here in the middle here, I'm going to go with the 17 volt pumping it that direction. Okay? So we'll call that path 2. Now how about over here at that third one? Yeah, let's go that. 14 pumping it that way. That'll be path 3. Now I hope those will work. I hope that'll be enough. And let's see. That says both this one and this one has current going that way. And that's good because that's how we chose I2. And both of these look like they have the current coming down this way. So everything's looking like, I believe we got all of our I's with the right signs. Okay? But guess what? If at the end of the problem you wind up with an I that's negative, that tells you you put the arrow in the wrong direction. Just flip it over and you got it right. Okay? So you could have a negative current. That just means you chose the direction wrong. It's looking here like we might get it right. But let's see. All right. Do you like the way I did before, or would you rather go straight to a current equation? Like before. Okay, where would you start on path 1? I'm going to go back to black here. Your junctions add or subtract currents. Your paths add or subtract voltages. So what you got here? 10. You start with the positive 10. You're going climbing up that voltage there. Then you have a minus. How about, yeah, can I just go to 2I1? Now that we know what the resistances are, let's go on and do it. I'm being really lazy. That was too much writing before. Okay, continue along that path, nothing down here. So go up here, what do I hit? Minus 4I2. Okay, and we've come back where we started, so that's equal to 0. Okay, you want to go on and translate that over here? Okay, what would that be? 2I2. Say again? Oh, I won. I'm sorry. Oh, no. Okay, hit the wrong button. Sorry about that. Doesn't take. Okay. See, my old package, I could have done that so much easier. That's a 2I1. I wasn't paying attention. 2I1 plus 4I2. I'm going to lose that. Oh yeah, I'm cheating. I'm combining things. Yuck! Get out of there. Okay. Okay. Did you get this? That's what we have. I mean, you see where this comes from. Okay. Now, what I'm doing here is writing it so I get it in matrix form. Now, to get it in matrix form, I want all my variables over the same variables, and I want my equal signs over equal signs, and I want my constants over constants. Here's my constant, okay? Here's my variables. So what I'm going to do is move the variables to that side, make them both plus, right? And then I'm going to switch sides. So that's going to be 2I1 plus 4I2, making those plus, equals 10. So that's going to be my equal 10, because that's my constant. See what I'm doing? Say again? Okay, it comes from here, okay. I'm going to get my constant on one side and my variables on the other. So I'm going to add a 2I1 to both sides of the equation. And now I'm going to add a 4I2 to both sides of the equation. Right? Okay? These add to 0, those add to 0. I have 10 is equal to 2I1 plus 4I2. And then I'll just flip sides. Yeah. All right? Now, just because I need the room, I'm going to erase that if it's all right. But I'll let you get all the time you want to write it. So let me know. Got it? Okay. Just because I have limited room here. That's why I'm probably shouldn't be, but skipping some steps. But okay. Let's go to path 2. Now you can start anywhere you want to. I kind of like to start, just because I like it, with the power supply, the voltage, the EMF, the potential difference, whatever you want to call that. And if I start here at the number 2 and start going around the path in a clockwise fashion, that gives me, I hit first a positive 17. Going up the voltage 17. And then I go down to I what? I what? I4, okay. I68, never mind. Okay. My pen's not writing well. Okay. What's the next thing I hit? Coming around path 2. Next thing I hit, I get R5, don't I? I drop voltage going across that resistor. Okay? And what will that be then? I'm dropping voltage, that'll be a minus. Help me? 2I5. Okay, keep going around path 2. I run into another resistor. Oh man. And it's in the right direction, so I'm going to drop I3. Now, it doesn't seem like that would be right, except that you have a 1 ohm written in front of it. You just don't write it down. All right. Oh, we're still not home yet. What else have we got? We got and you're going and drops another 4R2, isn't 4I2, isn't it? And then we finally back home at number 2, right? Okay, now, going to do the same thing I did before, but the order, I got to get it in the right order too. I don't have any I1s, I have an I2, and that's a 4. I'm going to move it to the other side. Oh, that equals 0. The sum of the voltages around a closed loop is always 0. Okay? So I'm going to move that to the other side. That's going to give me a 4I2. Okay? Then I've got a plus I3, right? From this one. Then I got a plus 2, and I put it in the wrong place, so let me go back and do that. Okay. Yuck. Okay. Plus, what was it, 2I5? 4. I had it right the first time. Goodness gracious. Okay. Yeah, 2I4. Where is it? There it is. Okay. Plus 2I4. Okay. And then we also have a 2I5. Okay. I was looking at the wrong one. Plus 2I5. And that's equal to, second, 17. See, remember I moved all the drops of voltages to the other side to make them positive. Rearranged them 4, 1, 2, 2, 2, 2. and then that left the 17 on the other side, and then I flip sides. Okay? Let's do pathway 3. Now, you can start anywhere you want to. I just like to start with the voltages. You don't have to. Don't fall into my patterns if you don't see them helpful. So basically, here's my starting point right there. And moving up, you get, first thing you get from here, going in the blue direction there, P3 direction. Second, you go up 14, right? Okay, that's where I started there. You can start anywhere. You can start down at 3, up at 4. You can start anywhere you wanted to. It'll work out fine. I just like starting at the battery, okay? So I go up 14 volts. What's the next thing I hit? Minus 2I5, right? And then what's the next thing I hit? Minus 4I6. Yeah. Now, second, and that's equal to 0 here. You're absolutely right. The voltage ups are equal to the voltage downs, okay? Now, let's rearrange it over here, and what would that be? Move these to the other side. That gives you 2I5 plus 4I6, and that's equal to 14, you said? All right, finally we got 1, 2, 3, 4, 5, 6, 7 equations with 6 unknowns. Tell you already one of these is unnecessary. We hope only one's unnecessary. If more than one's unnecessary, we don't have a valid system. Yeah, but let's see. Next thing I want to do is do my matrix, right? So I'm going to erase my scratch work down here if that's okay. Can I? Okay, so let's erase this because I got a lot of matrices to write. I'll probably wind up erasing just about everything, but let's erase as little as possible as we can to begin with. All right, so we need to translate that set of equations into a big old hairy matrix. Okay, that first one says what? 1. Second? First equation. This one here. 1. That's a minus 1. See? Oh, okay, I'm sorry. I thought you said another one. Okay, I can't hear well. Okay, got it. 0, 0, 0, 0. Because we have I4, I5, I6, all are zeros in that first equation, then the 0 on the outside. This is where I like to have my dashed line so I can see where is my equal sign. There it is. Okay. Second one. Negative 1, 1, 0, negative 1, 0, 0, 0. Next, 0, 0, negative 1, 0, 1, negative 1, 0. Next, 0, 0, 0. Right? Negative 1, positive 1, 0. Next. Say that one more time. I can't hear you. Reduce which one? Oh, the next one, before we write it? Absolutely, good idea. Okay? He's really getting lazy on us. I've created a monster here. Okay? So that next one's going to be a 1, 2, 0. Oh, you got to take that half of that too. I'm just kidding. Okay? 0, 0, 0, 5. That's this one right here. Okay? We divided by 2. Okay? Next. 0. Let's say the next one's a 4, right? So 1, isn't it? Yeah. Don't do the subscript, do the coefficients, okay? Next. 2, 2, 0, 17, one of my favorites, okay. Next. 0, ooh. I'm having trouble writing these because I get into my symbols. 0, 0, 0, one more 0 there. Then we got a 2. Oh wait, let's do that one too, okay? Come on, Manuel, you're letting us slip up here. Okay, that one we can divide by 2 too. We're just being lazy about it, right? Okay, that would be a 1, a 2, 7. Okay. All right. What do we want to happen first? A 1 in the upper left? We got it. All right. What do we want to happen next? 0 is below it. We only have to change 2. Okay. How do we change that first one? Yeah, row 1 plus row 2. Okay. So this becomes, I'm going to try to scrunch up some here. Okay. We're using row 1, so write it down. 1 minus 1, 1, 0, 0, 0, 0. Okay? Your new row 2 is what? 0, 0, 1, negative 1, oh, wait, 0, 0, 0. My pen is really slow here. I'm slow, but it's even slower. Okay. Now, what we already got a 0 there, so let's write that third row down. 0, 0, minus 1, 0, 1, minus 1, and 0. It drives me nuts. The fourth row already has the zeros there. Let's write that down. 0, 0, 0, 1, minus 1, 1, 0. All right. Now, what do we do with the fifth row? Is that fifth? Yeah, fifth. A little louder. Negative row 1 plus row 5. Okay? What will that become then? Zero. Okay. What that one becomes? 3. Next. Negative 1. What is that? Next one is 0. Next one's a 0. Is that right? Ah. One more 0. And then a 5, I believe, isn't it? Okay. All right. And we got zeros in the last 2, so I'm going to write them down. 0, 4, 1, 2, 2, 0, 17. I like that one. Okay. Next. 0, 0, 0, 0, 1, 2, 7. Right. Okay. So, We got our 1 here, 0's below. What do we want next? I want to go to another problem. All right. Because we want a 1 as the first non-zero entry, but as Jonathan said, we need our stash out, so we need one of these 2 rows to move up there. If we take this one up there, then you're going to have a 1 here, a negative 1/3 here, and a 5/3 there. If I move this one up there, you'll have a 1, a 1/4, a 1/2, a 1/2, and a 17/4. Which you reckon? That one. Okay. You got your wish, didn't you? Okay. Don't rub it in. All right. You got all your fractions. Okay. You lucky W. Okay. I think I'm going to have to erase some stuff because I can't possibly write all this stuff in. So let me do some erasing here. Just won't take that eraser. Okay, I'm going to erase those last 2 equations because they're in my way of writing. Goodness, this is slow. I guess I've got so much on the screen. It is? How did you let that happen? Okay, so now I'm feeling a lot better about it because I'll just say, you take it home and solve it yourselves, okay? You got a good start, go for it. And we'll pick up next time with, whoa, that finishes 1.3, okay? Now you can do some of the curve fitting if you want to. That's examples 1 through 11. We didn't do any particularly, but if that's something of interest to you, do a few. Then you could do any of the odds 13 through 25. And again, I'll let you decide if you want to do any of those. You don't have to, but if you want to, just to see how those work, if some of those problems look like they might be something that would be of interest to you in your field of study or in your future life or something, go for it. The network analysis, I think, makes a lot more sense for us to do. So I'll let you choose between 27 and 29. And then other network analysis, doing what we were just doing, I'll let you choose between 31 and 33. And then if you want another sort of fun application of it, number 35 is temperatures. And if you're going into a place that you might need that. Now, if you remember your good old Cal 2, when you did partial fractions, number 37 is another way to do that. So you could do that one. And then in calculus, and we may get to them, hopefully before the term's over, eigenvalues, or at least this looks like it could be an eigenvalue problem. So I'll let you decide whether you want to do 39 or not. Okay, now, the last time I taught this, I combined 1 and 2 together before I gave a test. What I think I may do this time is give a shorter test and get a test prepared for you just on chapter 1, because it turned out to be so late into the term before we got to the first test. I think I'll give you one. I don't have it ready now. I should have gotten it ready. Sorry. But I'll try to do. It won't be more than 10 questions. It may not even be 10. But I'll do, and they'll be relatively simple. Okay, I think. So we'll go from there. Some of them will be really simple. Okay, just to get you a good grade to go with your paper scores. Oh, that's right. Only one of you turned in a paper yet. That's right. All right, to bring up those paper scores. Okay, zeros. Okay, so I'll let you. And then since we're at the end, again, you can look at any of the odd number review exercises according to what you see there. Odd numbers in each section I'll let you choose whether you want to do some of those. They're well worth a shot, okay? And we'll begin next time with matrices, which is what we've been doing, okay? Chapter 2 is dealing with that. So, sound okay? So wrap up that last example.